We are looking at Module 3, Chapter 7. Chapter 7 covers estimating parameters and determining sample size. Number one, true or false, the confidence interval estimate of the population mean is constructed around the sample mean. All we have to do, look at the formula. Confidence interval is x bar plus minus E, where E is Z alpha over 2 sigma over square root of n, because sigma of x bar is sigma over square root of n. So the reasoning is the formula. Estimation means assigning values to a population parameter based on the value of a sample statistic. In general, we don't have access to the population and therefore any population parameter, so we start from somewhere. Where do we start with? With the sample statistics. For example, we are interested in finding mu. We don't have it. Where do we start? We start with x bar. So x bar is considered to be the point estimate for mu. The confidence level is denoted by 1 minus alpha, or 1 minus alpha 100%. The maximum error or margin of error, when sigma is known, it's the formula that is up here. Z alpha over 2, sigma over square root of n. The parameters of the t distribution is only degrees of freedom, and degrees of freedom is most of the time, not always, in some cases it's not, is equal to n minus 1. What criteria are required to apply the t distribution to make a confidence interval for mu? The sample must be a simple random sample, S or S. Either the sample is from a normally distributed population or n is large. How large is good? Larger than or equal to 30. And finally, the population standard deviation sigma is unknown. Find the value for t, for a t distribution with a sample size of 20 and a confidence level of 95%. Find the value of a t for a t distribution with a size of 30 and a confidence level of 90%. So I want to quickly go over how the table is used. Number one, when you want a confidence interval in between, you put the amount of confidence level, in this case would be 95%. So if I were to write the first one, then I would put 95% here. And this one would be 0.05 divided by 2, which is 0.025 on each side. Degrees of freedom is n minus 1. For this one is 19. And t becomes plus minus 2.093. How do we arrive at it? We will look at the table in a moment. In the second case, degrees of freedom is n minus 1. And the 90%, this one will be now 90%. And this one would be 0.1 divided by 2. See, 1 minus 90% is 0.1, which is 0.05, resulting in t being plus minus 1.699. How do we arrive at it? Let's take a look at the table. When we look up the t distribution table, it looks like this. We have on the left column degrees of freedom. There's not enough space, so I'm just giving you the degrees of freedom that we need, numbers 19 and 29. So you find first and foremost the degrees of freedom. In front of it, you see a bunch of numbers. Then at the very top row, you see area in one tail, area in two tails. So when you look at number 19, you want a 95% confidence interval. So the area in two tails is 0.05, or in one tail is 0.025. So take a look. This is what we get. For the second case, 90%, that means 10% in two tails, or half of it, 5% in one tail. And that's how we arrive at the answer. For a case like this, of course, you can use a calculator as follows. Second variables inverse t. So we put the area, degrees of freedom, enter, and I'm looking up only one of them. I'm looking up the second one. I didn't do the first one. One is good enough. For the first one, area to the left would be 0.025 chi-square. Find the critical chi-square value for 20 degrees of freedom when the area to the left is 0.01. Find the critical chi-square value for n equals 30 when the area to the right is 0.9. In the case of a chi-square, you need two things. You need the area to the right, and you need degrees of freedom to do the reading. So for question number 9, degrees of freedom is given as 20. Area to the left is 0.01. That means area to the right is 1 minus that. So degrees of freedom is given. Area to the left is given. We have to calculate the area to the right. We can draw it as follows. This is the given area. Therefore, we calculate the area to the right to be 1 minus that. So take a look. On the left column, we find the degrees of freedom. We go down until we hit number 20. Across that, we see a bunch of numbers. The area to the right we established is 0.99. What you see at top is the area to the right. Take a look at this graph, area to the right. So at the top, look for 0.99, and there you have it. Second case, n is 30. Degrees of freedom is 30 minus 1 or 29. We want the area to the right, which is given as 0.9. So that is 8.260. That's the previous one. Now we go down, we find number 29. Across from it, we find a bunch of numbers. We want the area to be 0.9. So go up here and look for number 0.9. And that's your answer. This is how you look up chi-square table. A statistician is interested in estimating at a 95% confidence level the mean number of houses sold per month by all real estate agents in a large city. It is known that the population standard deviation is 1.9. How large a sample should be taken so that the estimate is within 0.65? Find 95% confidence interval given the following if the mean of such sample size is 3.4. So when we read the question, what is given? We want 95% confidence interval. Sigma is 1.9. Part A, E is 0.65. I'm going to remind you of the formulas. Confidence interval is X bar plus minus E. Sigma of X bar, sigma over square root of N. E is the alpha over 2 sigma over square root of N. If you are interested in a sample size, when we solve for N in this equation, results in this one. So N is the alpha over 2 sigma over E, quantity squared. So 95% confidence level. 1.96 is a common number. It's something perhaps we should know. For a 95% confidence interval, we use this number for the z-score. So plug it in to this equation. Don't forget it has to be squared. Now, whatever number you get, it must be rounded up. In other words, it's 32.1 or 32.8 makes no difference. The answer in both cases is 33. Because we want, this is the least number we need. So we will always round up. Find this 95% confidence interval if the mean of such sample size is 3.4. X bar is 3.4 plus minus E, which is 0.65. What does it mean? We are 95% confident that the true population mean is between these two numbers. So one more time. We are 95% confident that the true population mean is between these two values of 2.75 and 4.05. A random sample of 20 female members of a health club showed that they spend on average 4.5 hours per week doing physical exercise with standard deviation of 0.75 hours. And we're going to assume normality, normal approximation. So before even we move on, what is given? N is 20. Now, pay attention to this. When it says average 4.5 hours, is it X bar or is it mu? If it pertains to all, becomes mu, but it pertains only to those 20, so therefore it's X bar. Same thing with this one. Standard deviation, is it sigma or is it S? If it pertains to the whole population, it's sigma, but it goes back to those 20, it's S. And that's the way you have to be careful reading to distinguish between S and sigma, X bar, and mu. What is the value of the point estimate of the population mean? I just mentioned that the point estimate of any population parameter is its corresponding sample statistics. For population mean is sample mean. Again, I have some formulas there for you. We're going to discuss that in a moment. Point estimate of mu is X bar, which is 4.5 hours. So point estimate for mu is always the value of X bar, whatever X bar is in that question. We are interested in finding the 98% confidence interval. That means over here, we have 98%. And over here, we have 0.02 divided by 2 or 0.01. So this area, each one is 0.01. That's the idea. Now, N is 20, degrees of freedom is 20 minus 1 or 19. And T alpha over 2 can be looked up from the table or technology. I went over the concept. Area in two tails is 0.02, in one tail is 0.01. We get those numbers. And now we want to calculate X bar plus minus E, where E is T alpha over 2 S over square root of N. Let's do that. So we calculate the value of E by plugging in everything that we have. T we just found, S is given, N is given. So plug in. That's why it's important to write the given. When we go with the formula, we know what we are putting in. And now we are going to subtract and add this number to X bar, resulting in the following. So based on our data, we are 98% confident that the true population mean is somewhere in between. So based on our data and our calculation, we are 98% confident that the population mean is between these two values. Let's look at TI calculator and how we use confidence interval. So T interval, stats, X bar, 4.5, S 0.75, N 20. We want 98% confidence. Everything is given plug-in. It gives you the answer, 4.0742. They have it for 1, 4.9259. We have it 4.9258. It's just a matter of calculator being more precise. Out of 500 randomly selected adults, 300 said they were in favor of the death penalty for a person convicted of murder. What is the value of the point estimate of the population proportion? What is the 95% confidence interval for the population proportion? Out of 500, n is 500. 300 are for it, that's x. You are dealing with the binomial distribution with the n and x as follows. So that's understanding the situation and the given. Here's some formulas. Confidence interval is p hat plus minus e. Sigma of p hat square root of p hat q hat over n. E z alpha over 2 square root of p hat q hat over n. And if you solve this one for n, gives you z squared p hat q hat over e squared. By the way, mu of p hat equals p also. Now, what is the point estimate of the population proportion? We don't have a population proportion. Where do we begin? We begin with the sample proportion. We begin with p hat, which is x over n. So point estimate of p is p hat. P hat is x over n. So everything has a formula. I'm mentioning that because you want to see where everything comes from. Justification for the work. 95% confidence interval. We want to get to p hat plus minus e. The very first thing for a 95% confidence interval, we need the z, and the z score for 95%. We've been using it as 1.96. Everybody remembers that from the previous questions. Therefore, calculate the e first. We have the z, which is 1.96. P hat 0.6. Q hat is 1 minus p hat. And plug in. 1.96 square root of 0.6 times 0.4 over 500, we have the answer. That is the E. We are going to add and subtract this number to the P hat. That gives us the confidence interval. So P hat is 0.6, subtract from it, add to it, and there we have it. Now, what does it mean? We are 95% confident that the true population proportion is somewhere between. All right. TI calculator, calculating the confidence interval. One proportion Z interval. You plug in the value of X. And we want 95% confidence interval, and it gives us the answer that we got here. Again, you have to justify your steps accordingly. How large a sample is needed to be 99% confident that the margin of error is 0.025 for percentage of golfers that are left-handed, if we assume that 15% of the golfers are left-handed based on a previous study. So what is it we want? 99% confidence interval. E is 0.025, and we are assuming in this case P hat is 0.15. Needless to say, Q hat becomes 1 minus that. For 99% confidence interval, also we can look up a table or technology. This is a common value of 2.575. Q hat 1 minus P hat. So that's 0.85. Now let's plug it into this formula. This one is replaced with 2.575. P hat is replaced with 0.15, Q hat with 0.85, and E with 0.025. Don't forget the denominator must be squared. And this will always be rounded up. So 1,353 is the minimum number we need. How large a sample? At least this much, so that's why you round it up. Assume that we have no prior information, in which case we don't know p hat is 15%. We assume the worst case scenario, p hat equals q hat equals 0.5. So in this formula, if you choose p hat equals q hat equals 0.5, their product is 0.25, the product of these two. Gives you 0.25. You calculate the work, you end up with a more conservative estimate, a larger number. This must always be larger than this, otherwise we've made a mistake. And notice, minimum we need this much, it doesn't matter, it's 0.2 or 0.8 or whatever we round up. And instead the X bar is 80.5, S is 4.6, assume normal population, find 98% confidence interval. For population variance and standard deviation, here's the formulas. Sigma squared is between n minus 1 s squared over chi squared of the right and n minus 1 s squared over chi squared of the left. Now sigma, this is variance. Sigma or standard deviation is the same thing, take a root. So degrees of freedom, okay, so we look at this concept, we want 98%. So this is 98%. Remember, for chi squared, we need the area to the right. So for chi squared of the right, the area to the right is 1%, and that's fine. In other words, let's just do this. So this is 98%, which means we have 1% on this side, 1% on this side. For chi squared of the right, the area to the right is 1%, degrees of freedom is n minus 1, which is 30 minus 1 or 29, we are good to go. For chi squared of the left, we want the area to the right, which is 99% or 0.99. That's the thing you want to be careful of. Therefore, degrees of freedom is 29, 98% confidence interval, subtract from 1, you get 0.02. So for chi squared of the right, the area to the right is 0.01. But for chi squared of the left, the area to the right of that is 0.99. Why is this important? Take a look at this one. You have the degrees of freedom on the left side. You look up and you find number 29, and those are the numbers. Those are the numbers. Then you go at top and you look up these two values, 0.01 and 0.99. This is 0.99. This is 0.01. Therefore, chi squared of the right is 49.588. For the left is 14.257. Plug in. N minus 1 is 29. S is 4.6 squared. So that's the numerator for both cases. Chi squared of the right, you put them here. Chi squared of the left, you put them here. You do the math. So pay attention to the formula and plug it in. Results in the following. That means we are 98% confident. The true population variance is somewhere between 12.3748 and 43.0413. For sigma, you don't have to do much, just take a root. So we are 98% confident. The true value of variance is between 12.3748 and 43.0413. We are going to take a root of both sides. Sigma between 3.5178 and 6.5606. Therefore, we are 98% confident the true population standard deviation is somewhere between 3.5178 and 6.5606.